So the last few chapters we spent talking about matter and how matter is divided into two different classes, a mixture and a pure substance, and then we talked about atoms and all these little atoms and what's into the atom and how that makes up all of the matter. Now we're going to look at how you count matter. Okay? Well, to look at this, we're going to look at some ordinary examples for counting units. And you can have things like a pair, or a dozen, or a ream, or a gross. So I can have a pair of boots. I can have a pair of eggs. I can have a dozen eggs. I can have a dozen boots. I can have a ream of paper, or a gross of pencils, or a gross of paper. And all of these are what we call counting units, where I can know exactly how many I have in there without having to sit down and count it. A pair always means 2. A dozen always means 12. A ream always means 500, and a gross is a dozen dozens, or 144. Well, just like those counting units, we have a counting unit for matter. We have what's called the mole, and it is the SI base unit to measure the amount of a substance. And a mole just measures the amount of atoms, molecules, or formula units that are in a substance. So we need this mole unit because atoms are so tiny. I mean, we can't see an atom. We have to have these really expensive, really large microscopes to be able to see an atom. So I don't want to have to sit there and count them all through a microscope. So we have what's called a mole, and we're going to relate that to grams later, because grams are what we can see. But for right now, we're just going to stick to the mole and how many atoms are in a mole. So what they did was they took 12 grams of carbon-12, and we used that carbon-12 back in the isotope video, because that's what they based the AMU on, or atomic mass unit. Now they took 12 grams of carbon-12 and decided, okay, that's how many atoms are going to be equal to a mole. And it has been established in those 12 grams of carbon-12 that there are 6.0221367 continuing times 10 to the 23rd particles, atoms, ions, molecules, or formula units in 1 mole. And we call this number Avogadro's number, and it's in the honor of Amedeo Avogadro. We did a lot of work with atoms and molecules. So we're going to start off then with converting a normal unit or an ordinary unit, something that you are very familiar with. And we're going to start by converting dozens. If I, for example, want to know in 3½ dozens, I have how many eggs? So if I have 3½ dozens, all I do is multiply that by 12 to get the number of eggs that are in those 3½ dozen. Because I know that there are exactly 12 eggs in 1 dozen. Well, our mole number works the exact same way. It's just a way, way, way larger number. And just like a dozen can be used for anything, like a dozen papers, dozen books, dozen pencils, doesn't matter, a dozen is still 12. A mole works the exact same way. And what we have here are my mole jars, and each one of these is a mole. So this is 55.8 grams of iron, and that's 1 mole of iron. I can have 32.1 grams of sulfur, and that's a mole of sulfur. I can have 207.2 grams of lead, and that's a mole of lead. I can have 63.55 grams of copper, and that's a mole of copper. Or I can have 294.22 grams of potassium dichromate, and that's 1 mole. Notice how each one of these looks different. Okay? There's different masses involved. They aren't the same shape. They aren't the same size. But all of them are equal to 1 mole because there are that many particles in them. It's not telling us anything about how the particles are arranged, which is kind of how we get all the grams, but there are exactly that many particles in that mole. Each one looks different though. So a dozen pencils will look different than a dozen note cards or a dozen eggs. Look different, have different masses, all represent a dozen. Same thing here with the mole. So let's go ahead and look at some examples. The first one there says how many atoms are in 2.5 moles of zinc? So what you do is you think just like a dozen. Okay, if I had 2.5 dozens, I would multiply that by 12 to get my number of items. Well, here I'm just going to atoms. So I have 2.5 moles, and I know that there are 6.02 times 10 to the 23rd particles or atoms in a mole. So I take that times 6.02 times 10 to the 23rd. You can also look at it as a ratio and say if I have 2.5 moles, I want to know how many atoms that is. Well, I know that in 1 mole, there are 6.02 times 10 to the 23rd atoms. And then all you would do is cross multiply. Anytime you have a ratio with an equal sign in the middle, you got to cross multiply and then divide. But I'm just dividing by 1. So I'm multiplying in both of them here. You either have to show me that you are multiplying or dividing or write out the ratio. Now you've got to be careful how you plug this into your calculator. You can actually plug in the 6.02 times 10 to the 23rd, but then you'd have to have parentheses and you'd have to be really careful with that. It actually is a lot easier if you have a graphing calculator. If you take 2.5 and if you plug in your 6.02, there's a little E key and you put 23. So my calculator there has a little E in it. Mine's the EE key, mine's an actual key, but on your TI-84s or the silvers, whatever they are, it's usually a second something. And it'll say like second, I think it's x to the -1. But you want to see that E on your calculator. You've seen it before when you get an answer. Okay, if you plug an answer in, or if you plug in 6.02 times 10, and you do the caret 23, so I plug it in like this, you're going to run into the problem of it's going to take it times 10 more than once. So I really would suggest against using that. Use the E key. It's times 10 to all in one. Okay. Well, when I do that and I multiply it by 2.5, you should get an answer of 1.51 times 10 to the 24th atoms. And it's going to be atoms of zinc. The N. Well, let's try another one. If I have 3.25 moles, and that's of silver nitrate, it's just AgNO3. We'll look at the naming for that later. Same thing. I'm going from the mole to the number of items. So I multiply by 6.02 times 10 to the 23rd. And again, be very careful. Put it in your calculator with the E in it. And it's not this E, the lowercase, but it should look uppercase. Because you don't want to take an E to the something. Plug it in just like that, and then you get out your answer, which should be 1.96 times 10 to the 24th. And actually, that should be molecules. AgNO3 is a compound. Compounds are measured in molecules. But the number is the important part here. Well, what about if we go the other direction? So now say that I have 2.50 times 10 to the 20th atoms of iron, and it wants to know how many moles that is. Well, just like we were doing before, you can think it through a little bit and think, okay, my number should be getting smaller here. I'm not going to be multiplying, so which means I'm going to divide, or you can take your 2.5 times 10 to the 20th atoms and set it up as a ratio and say that's going to be some number of moles equal to 6.02 times 10 to the 23rd atoms in 1 mole, and you're still going to end up dividing because I cross multiply and then I divide. Again, be careful when you plug it in your calculator, but we should be getting here 4.15 times 10 to the -4th moles, which is the same thing as 0.415. Same thing as 0.000415. You don't have to write it in scientific notation, I just tend to. The last one here, if I have 3.75 times 10 to the 24th molecules of CO2, how many moles does this contain? Same thing. Divide by 6.02 times 10 to the 23rd, just like you would divide by 12 if I was going from items to dozens. Divide by what the number stands for. You should get 6.23 moles. Again, if you don't remember whether to multiply or divide, set up a ratio. Okay.